Hello, this is section 3.5 in Calc AB, and we're going to be doing a summary of curve sketching. And what I love about this section is it's just in time for if you're still trying to wrap your brain around the relationship between when the derivative is increasing, what that means, or the derivative is positive, what does that mean? And it also helps you make sense of the first and second derivative test, and it's a really a good section. If you're still struggling a little bit with kind of understanding what we're doing, this will help tremendously. So the following checklist is intended as a guide to sketching a curve y equals f of x by hand. Not every item is relevant to every function, for instance. So you might have a polynomial function and we don't need to know asymptotes, obviously, and stuff like that. Okay, and sometimes symmetry is helpful in knowing when you're sketching a function, but usually symmetry is one where I'm like, oh, yeah, I could have used symmetry. I'll realize it after the fact. So, okay, but the big thing, when you're sketching a graph, which you've already done these, you did these in pre-calc and algebra 2. Does this look familiar, graphing this? So remember, you would first figure out where it crosses the x-axis. So here, we'll just talk through and then we'll go back and read through this box. So if you're graphing this function, pretend like you don't know any calculus yet. Well, you would first figure out where it hits the x-axis. So that's what we do first. Notice we factor an x out and factor it, and you get here. And remember, multiplicity played a role in it. So you'd plot your zeros at 0 and 3. And then from there, we would then figure out where does it cross the x and y axis. Well, you'd plug 0 in, and that's what we did here. We set it equal to 0. So when you plug 0 in, you get 0. So, and then from there, that's all you would know. You would then do the end behavior. It has a degree 3, so it ends going up and it's opposite. So you would start here, multiplicity 1, so you'd get to go straight through, then you'd curve around, bounce, because it has a multiplicity of 2, and then it has the correct end behavior, and you'd be done. But we never knew exactly how high to go when we curved back around to bounce off of 3, and that's what we can finally do. We can finally get these relative max and mins. We can finally get the accurate inflection points and actually truly do a better job of sketching these graphs. That's what this section's about. All right, so let's do that. So from there, well, let's figure out how exactly high we're going to go on that relative max. So we would do the derivative, which I already gave to you, set that equal to 0. Where is the slope of the tangent line horizontal? Those are your critical numbers. So we did that, and here's that first derivative number line test. And this will both tell us where the relative extremes are, and it will tell us where the function is increasing and decreasing. Then we set the double derivative equal to 0 for any potential inflection points, and we get 1 at 2. So I made a double derivative number line, put 2 on there, and that'll help us test for concavity. So plug these intervals into the second derivative. Remember, on this one, you plugged these intervals into your first derivative. And this will tell us where the function's concave down and up, and because we changed concavity, we do have an inflection point there. So from here, we have our relative max and our relative min at 1 and 3, which I showed you here. And we have an inflection point at 2. Remember, plug these numbers 1, 3, and 2 back into your original function to get the ordered pairs. And there we go. But we're finally able to graph. So plot these points. So we'd already plotted the 3, 0. We need to plot the 1, 4. That's our relative max. And then we plot the inflection point 2, 2. And then we're able to get a better representation of the graph. Okay. All right, so that's basically what this section is. It's lots of examples of different type of curve sketching, but using this first and second derivative to help you figure out where the function's increasing and decreasing, where the function's concave up, concave down, and actually graphing the correct ordered pairs, getting all your relative max and mins on there, get all of your inflection points plotted. So I want to scroll back up to this box. So before you do your curve sketching, always think through the domain and range. Mainly the domain helps us. Are there any asymptotes? Is there a restriction on the domain? Make sure you get your intercepts on there. Now, the symmetry I was telling you earlier, that's something I usually realize after the fact. But if it's helpful, if you happen to notice, asymptotes, both for horizontal and vertical, max and mins values, these are your relative extrema, increasing or decreasing, and then inflection points. You need to make sure all of this gets on your graph. Okay, so let's look at another one. So this is a rational function this time. So start off normal. Where does it hit the x and y intercepts, and are there any zeros? That's what you've done before calculus. So set this equal to 0, and you notice right off the bat, here's me setting it equal to 0. You'll get 0 from the numerator, and then from the denominator you get plus or minus 4. Those are your asymptotes. And then if you plug 0 into the function, you also get 0. So I plotted that point 0, 0, and then I went ahead and plotted our asymptotes. And because the degrees are the same, that's what this is not equal to 1/2. I shouldn't. This is me going off to the side saying, oh, our horizontal asymptote is equal to 1/2. This is not equivalent. Actually, I know why I did that. I'll go explain that here in a second. So 1/2 is your horizontal asymptote. Now, there was one other extra thing you did when you were in Algebra 2, and that is you set the rational function equal to the horizontal asymptote to see if it crosses. The nice thing is you'll know, because if it crosses the horizontal asymptote, that'll create a relative max or min, because then it curves back to then approach the asymptote as you go off to infinity. So that'll show up in your calculus if it does cross the asymptote. Okay, so now that we've got our basics, we have our asymptotes, our zeros. Now let's actually figure out where our relative max and mins are and where we have points of inflection. So set your first derivative equal to 0, and you get 0 from the numerator, and you get the plus or minus 4 from the denominator. But remember, to be a critical number, it has to be defined on the original function, and those are vertical asymptotes, so you do not include those as critical numbers, just 0. But you do put those on your first derivative number line test, because you could change from increasing to decreasing or vice versa at those asymptotes, which happens. Well, not really. Never mind. Well, it goes from increasing and it's increasing, but it can happen where it changes. Okay, so I set up my number line here. 0 is my only true critical number, but I'm able to test these intervals in the first derivative to figure out what's going on. So we're increasing, increasing. We go from increasing to decreasing at 0, so we have a relative max there, and then decreasing, decreasing. Then set your second derivative equal to 0 to get your potential inflection points, and you don't get anything out of the numerator, and you get plus or minus 4 from the denominator. Okay, but remember though, that plus or minus 4 are asymptotes, so you don't have any potential inflection points. But again, you still want to create that double derivative number line, because you can change concavity at those asymptotes. So that's what I've done. And there you go. So from there, I can use this information. I'm concave up until I get to -4, and I'm increasing. So that's this. Now between -4 and 4, I'm always concave down, but I go from increasing to decreasing. So that's this part. And then lastly, I end decreasing concave up. And the only point that actually really truly plotted on the graph is that relative max at 0, 0. Okay. All right. So, and then here's just some more interesting examples. So this one's interesting because it has an oblique asymptote. So again, started off the same, plug in 0, set it equal to 0 to figure out where it hits your axes, and it actually only hits here at 0, 3. That's the only place. Then get your asymptotes graphed. So we have a vertical asymptote at 3, and when you do long division, you can figure out, remember it's this up here, -x is your oblique asymptote. So I went ahead and plotted our asymptotes. Okay. Then once I've got the asymptotes are your blueprints, and make sure you get your intercepts. Then you dive into the first and second derivative. So set your first derivative equal to 0, figure out what's going on. You actually get 0 and 6 from the numerator, and the 3 from the denominator we throw out because remember it's not defined on the original function. These are your critical numbers. this is all going to go on your first derivative number line, even the 3, even though it's undefined. And then set your second derivative equal to 0, and the only thing you get out of that is the 3 from the denominator. But again, that still goes on your number line, but note to self, we have no inflection points. Okay, so test your intervals and the first derivative to figure out where you're changing from increasing to decreasing. And at 0, you realize you have a relative min. 3 is undefined. And at 6, you go from positive to negative. So increasing to decreasing, you have a relative max. So plot those 2 points on your graph. And then this confirms our double derivative is positive, so we're concave up. And yeah, we're approaching our asymptotes until we get to 3. And then past 3, we're always concave down, which again makes sense. Oh, isn't that cool how the calculus lines up with what you did back in Algebra 2 and pre-calc? All right, so here's another one. What I like about this example is you have different horizontal asymptotes. So when you first start it, you get your zeros. I mean, well, you get your zeros and you set it equal to 0 and plug in 0 is what I'm trying to say. So when you plug in 0, you get 3 halves. So that's what I plotted here. And then, of course, the denominator is never going to equal 0. Okay. But what's interesting is the limit as x approaches infinity. As you go off to infinity, remember a number over infinity is 0. But when you go off to negative infinity, that sends this e to the 2x to the denominator. So it makes it 1 over infinity, which is 0. Well, then that becomes 1 plus 0 is 1. So 3 over 1 is 3. So as you go off to negative infinity, you actually have a horizontal asymptote of 3. So that's an interesting graph and a good review of your limits. I think that was from section 1.6, I believe, chapter 1. Okay, so we kind of have our asymptotes sketched for us. Set your first derivative equal to 0. We don't get any critical numbers out of it. And really, there's nothing to put on your first derivative. This is always a decreasing function. You can plug in any number you want to figure out what's going on. And when you set your second derivative equal to 0, you do actually get 0 as a potential inflection point. And when you test your concavity, you do actually change concavity there. It's a smooth inflection point. Remember, had it been a horizontal inflection point or a vertical inflection point, it would have shown up as a potential critical number. Okay. So just a really interesting graph. And then here's one where you have to be careful with your factoring. This one you can go through and look at. It's got a nice little. I tried to put interesting graphs in the notes. I'm seeing if there's anything I want to point out. Here's another one. Here's a trig one. Here's the one where I have you fill in the information and use your graphing calculator. So get out your graphing calculator and see if you can get all these numbers from your calculator. Okay, and then lastly, here's just one more example, graph of the first derivative. So these can be a little bit challenging. This is the graph of the first derivative, and I always highly suggest you label the graph so you know exactly what you're looking at and you don't get confused. So if this is the first derivative from -3 to 9, use the graph to answer. So on what intervals is the function increasing? You have to immediately think, when is that derivative, or I said increasing, sorry. When is the function decreasing? When is the derivative negative? And that's over here. That's this part of it, -2 to 7. On what intervals is the function concave up? That's when the derivative is increasing. Okay. At what x values does the function have a relative extrema? So when is your derivative equal to 0 and what's happening? So at 0 here, when it crosses the x-axis, I go from positive to negative, I have a relative max. And here it goes from negative to positive, I have a relative min. And then finally, at what x values does the graph of the function have a point of inflection? When does your derivative change direction? When does it go from decreasing to increasing or vice versa, increasing to decreasing? And that's right here. So you have to think through what is your derivative graph doing, and you have to know these relationships. And I highly suggest you make flashcards to help you. Okay, so email me if you have any questions and make sure you practice doing these problems without your calculator first. Okay.